Assalamualaikum, my name is Nazim and I will be presenting about chapter 2. As you can see, the manual solution of the chapter 2 for question 2.1, optical sensor calibration, cubic nonlinearity, fx equals to x cubed plus 30x minus 30 equals to 0, and then we got 0x0 equals to 0, and then this is the manual solution for question A, fixed point iteration method. And finally, we got the conclusion: the method converged to x equals to 1.0000 in 5 iteration, which means the approximate error is around 0.03% and 0.05%. As for the Numerix method, I0 we got 0, I1 first iteration we got 100% approximate error, and then the second we got 3.3197%, and for third iteration we got 0.0100%. From the conclusion, the method converged to x is 1.000 in 3 iterations, which means the approximate error is around 0.01% to 0.05%. As you can see, this is the comparison and the microcontroller between fixed point and Numerix. The comparisons will be defined from numbers of iteration and the complexity. And as you can see, this is the details that provided for the comparison. And now I'm gonna explain about the MATLAB code for question 2.1. As you can see, the code is divided into few subsection, which is fixed point iteration method, the code for fixed point iteration method, and then as you can see the fixed point iteration, as you can see in the end, the fixed point iteration converge at the percentage of iterations. And then finally we have the code for approximate error, and then proceed to the second part, which is Numerix method. Well, the second part continues here. Here we got the code for the second part, which is part B, and then finally we have the comparison, which is the coding for comparison between fixed point iteration and Numerix, and then we have the graph for both comparison. As you can see on this picture, we have the code for second subplot, which is convergence comparison, and then they have line width and the marker size, and then they goes for iteration number and percentage error, and then we have convergence rate comparison. As for the legend, we have fixed point, linear, Numerix, quadratic, and then the location, which is northeast.
Good day everyone. In this part, we will explain the manual solution for this question. So, the record data shows the relationship between depth and pressure. The depth values are 0, 2, 4, 6, and 8 and 10, while the corresponding pressure readings are 101.3, 121.1, 140.8, and so on. The aim of this calculation is to estimate the pressure when the depth is equal to 3. For the first method, I use the third order Newton divided difference method. Since the required value is depth 3, I selected the nearest 4 data points, which are 0, 2, 4, and 6. These points were used to perform a third order interpolation polynomial. After calculating the divided difference and submitting x equals 3 into equation, the estimate pressure obtained was 130.975. Next, I'll also use the third order Lagrange interpolation method to verify the answer. The same for data points were used. In this method, each Lagrange basis function was multiplied with its corresponding pressure value. After substitute x equal 3, the final pressure value obtained was also 130.975. From both methods, the estimate pressure at depth 3 is the same, which shows that the interpolation was done correctly. So for the question comparison, Newton divided difference is more flexible if a new sensor or additional data point is added, because the previous calculation can still be used and only one extra term needs to be added. Lagrange method is less flexible because adding a new data point changes the whole polynomial to the calculation needs to be repeated from the beginning. So in conclusion, both methods give the same pressure estimate, but Newton divided difference is more suitable for updating sensor data in practical monitoring. So next we go to MATLAB solution, question 6.5. So our coding is same like manual solution, which is follow the step by step the manual solution. So I think that's all from me. Thank you.
For question A, we solve the system of linear equation using the Gaussian elimination method with partial pivoting. First, the coefficient matrix was transformed into an upper triangular matrix through the elimination process. Next, partial pivoting was applied by selecting the large coefficient in the column as the pivot element. This step helps improve numerical stability and reduce computational errors. After obtaining the upper triangular matrix, we perform back substitution to calculate the unknown variable. The final solution obtained were x1 equal negative 1.0006, x2 equals 0.9993, and x3 equals 3.0011. This value represent the accurate solution of the system after applying Gaussian elimination together with partial pivoting. Next, for question B, we use the Gauss-Seidel iterative method. Initially, all variables were assumed to be zero. Using the Gauss-Seidel equations, the value of x1, x2, and x3 were updated repeatedly through iteration. After the first iteration, approximate value were obtained. The process was continued for the second iteration to improve the estimates. After two iterations, the result were x1 equal 2.3806, x2 equal 2.8696, and x3 equal 0.3749. This value from question A because the Gauss-Seidel method is an iterative technique and only two iterations were performed. More iterations will normally produce results that are close to the exact solution. Moving on to question C. For question C, we discuss why partial pivoting is important. In this problem, the first coefficient. Next, I will present the MATLAB coding and result for question A. MATLAB was using to verify the manual calculation obtained using the Gaussian elimination method with partial pivoting. After running the program, the solution obtained was consistent with the manual calculation. The result were x1 equal negative 1.0006, x2 equal 0.9993, and x3 equal 3.0011. Therefore, the MATLAB result confirmed the accuracy of the manual solution for question A. Next, for MATLAB coding and result, question B. MATLAB was also used to perform the Gauss-Seidel iterative method. The program carried out the iteration process and produced the following result, which is x1 equal 2.3806, x2 equal 2.8696, and x3 equal 0.3749. These results are consistent with the manual calculation obtained after 2 iterations.
Assalamualaikum warahmatullahi wabarakatuh. My name is Rahim Abdul. My number matric is 72070. Today I want to explain a manual solution. Manual code for chapter 5. My question is 5.4 room temperature response. So, question A, determine the room temperature at T equals 0.6 using Euler method and midpoint method. So, from the program, we arrange the equation to find the slope formula. The slope formula FTT equals 300 minus TGT. Step size H equals 0.2 and start point T0 equals 0, T0, 0. For the Euler method, slope equal 300 minus 3 equals 300, which is T1 equal 0, so 0 plus 0.2, 300, so the answer is 120.00. For the step 2, 3 equal 0.2, so the slope equals 300, 130. So the answer is 187.2. So for the midpoint method, use half step 0.1 second to find my point temperature, calculate my point slope, then take full step 0.2 second. The main point slope is equal 600 minus 3, so the answer is 160.9776 Celsius.
Okay, so for question B, determine the relative true error of T equals 0.6. The real true answer, instead of guessing step by step, we plug T equals 0.6 into the exact calculus formula to find the flawless real world temperature. Formula 3 T of 0.6 equal 200 times, open parenthesis, 1 minus e to the negative 1.8, close parenthesis. The true value 166.9402 Celsius. Measuring how far off we are, to find the error percentage, we check how far our guesses are from the true value using this formula. Epsilon T equal the absolute value of true value minus absolute value over true value times 100%. For Euler method error, 160.9402 minus 187.2000 over 160.9402 multiply 100. So the answer is 12.13. So for my point method error, 168.9402 minus 160.9776 over 160.9402 multiply 100%. So the answer is 3.50157.7%. So for C, based on the error obtained, comment on the accuracy of the two methods. The main point method is more accurate than the error method. This is because the main point method uses the step slope at the middle of each interval, giving better expression of the actual solution. Okay, so for the MATLAB code, we use a ruler and midpoint method to solve the temperature ODE at S. Ruler produce 187.20 Celsius and midpoint produce 160.98 Celsius. Comparing with the exact value of 160.94 Celsius, the relative error will 12.14% and 3.57% respectively. This shows that the midpoint method is more accurate than the Euler method. So that's all. Thank you.
For question A, we begin with um, integrate the equation, the formula to fs equal to e power of x over 1 plus x power of 2. Then we enter f0, f0.5, f1, f1.5, and f2. Okay, next we go to n. We will do the interaction of n equal to 1, which is h is equal to 2. And then we will then go to the n equal to 2, h equal to 1. For T1, we got 2.4778. For T2, we got 2.5980. And then we will continue to n equal to 4, h equal to 0.5. Thus, we get T4 is equal to 2.6480. Okay, for question B, we will do the Romberg integration. R11 is we get R11 is 2.6381. R21 is we get 2.6647. R22 is 2.6665. C is when true value is 2.9460, and we can calculate the true value by the true value error. For the trapezoidal, we can get to 10.564%, and for the Romberg integration, we get 9.4874%. Thus, we can make a conclusion in question D. Romberg is more accurate because the percentage error is much more smaller. For MATLAB solution for question 6.5, for part A, trapezoidal rule, and one we got 2.4778, and two we got 2.56980, and four we got 2.6480. For question B, for part B, we got Romberg integration table, which is we got 2.6480, 2.6647, and 2.6665. And part C, percentage to error, we got trapezoidal error, we got 0.6826%, and Romberg integration, we got 0.0113%. Thus, we can make a conclusion that for part D, that the more accurate method is Romberg integration, as it yield a lower percentage true error.